In the name of God. Hello, dear students. My name is Masood. I'm a physics teacher. We are in Ferhua's website at your service to present lectures of physics curriculum grade 10. So far, we talked about some sections in chapter 1. In previous lectures, we talked about accuracy and precision. Right now, we have new subject. We have significant figures, or simply we can say sig-fig. Let's dive in with this lesson. What's this significant figure or sig-fig, right? Significant figure, let me read the definition and I'll explain it for you. It says those digits in a measurement that are known with certainty plus the last digit that is uncertain. So, or I can say those figures that include all certain figures in addition to one final uncertain figure. What does it mean? For example, we have a number here, 70.4. Significant figure actually consists of two parts. This part, let's say, it consists of two parts. This part is called, let's say, certain part, certain, right? It doesn't change a lot, but this part is uncertain or estimated part, uncertain or estimated part. This is called significant figure, right? So it consists of two things. The first part is certain, and it's followed by what? It's followed by an uncertain part or estimated part. So here 70 is a certain figure and 4 is the estimated figure. This one may be changed 4 may be changed to 5, or maybe it changed to 3. Think about, for example, whenever you want to weigh yourself. Whenever you want to weigh yourself by, let's say, balance, you see that that this part does not change. 70 remains as it is, but 4 becomes 5 and it reduces to 3. That's why we say it's uncertain or estimated part, right? This about significant figure in general. Excuse me. About the rules. So how do we calculate a significant figure? Let me tell you some important notes about significant figure. Keep in mind that non-zero figures are significant. So non-zero figures are significant. Like what? Like 1, 2, 3, 4, till 9. Except for 0. 0 sometimes is significant, but sometimes it's not. So keep in mind that every non-zero figure is significant. But we have a problem about the zeros. Zeros sometimes are considered significant, sometimes not. But we have a rule, actually. We have four rules. We have a table here about the rules of calculating, let's say, zeros, about the rule of, let's say, rule of determining 0 as a significant figure or not. Let me read the first one. The first one, zeros, number 1, zeros between digits. They are called middle zeros. Are what? They are significant. Like what? Like this example. 2.005 has 4 significant figures. So we counted the zeros as what? As significant figure because they are middle zeros. So keep in mind that middle zeros are significant. These zeros sandwiched by 2 and 5, right? That's why they are significant. So it has 4 significant figures. Another example, let's say 10,007. 10,007 has 5 significant figures. Why? Let's say, why do we consider them as significant figures? Because they are what? Because they sandwich by 1 and 7. Because they are located between the figures. That's why middle zeros are significant. Let's move on to another note. Number 2, another rule. In front of zeros in front of non-zero digits, or in other words, we can say leading zeros are not significant. So zeros in front of the figures are not significant. Leading zeros are not significant, right? We don't count them as significant figures. So here in this equation, in this question, in this actually numbers in this figure, we have this number, right? 0.00006 has only one sig-fig. I told you sig-fig is the abbreviation of significant figure. Only 6 is significant. Why? Because other zeros are located in front of the number. That's why they are not, let's say, significant. What do you say about this one? Think about it. Leading zeros are not significant. So that's why we have only 1, 2, 3 sig-figs. Let's move on to another rule. Number 3, at the end of the decimals. Zeros at the end of the decimals are what? Are considered significant figure. They are significant figures. We can name them as trailing zero within the decimals. So I separated into two parts. Trailing zero. These, let's say the number, number 3 and 4 is about what? They are about the trailing zero, but number 3 is about trailing zero within the decimals. Number 4, trailing zeros within the integers, within the whole numbers. About the number 3, actually, at the end of the decimals, zeros at the end of the decimals, or trailing zero. They are trailing zeros, right? Think about it. Let me change the color here. I want to change the color. About the trailing zero. Do they, let's say, count as significant figure or not? Of course, they are significant, yeah? Trailing zero at the end of the decimal. That's why they are significant. You have to count them. So 1, 2, 3, 4, 5, 6 sig-figs are there in this example. About under 1.50 has 3 sig-figs. Why do we count, let's say, 0 as significant figures? Because it's trailing zero, especially in, let's say, in decimals, they are considered significant. About the last one, at the end, zeros at the end of the whole numbers or integer numbers, or we can say trailing zeros within integers. They are not significant. So whenever you have an integer number, if the number is followed by a lot of zeros, these zeros are not significant. They are not, because they are trailing zero. So trailing zero within the decimals are significant, but trailing zeros within the integers are not considered sig-figs, right? So we have this number. Let me read the number for you. 2 million. Yeah? 2 million has one sig-fig. Only it has one sig-fig. Why? Because here we have integer number, right? Because we have integer number, we don't have decimal point. If we have decimal point, all of the zeros are considered sig-fig. But here we have integer. What do you say about this one? Does it have 2 or 3? I say it's 3. It's 3 significant figures. Am I right or wrong? Think about it. So we have trailing zero, right? That's why this trailing zero does not count. Yeah, ignore it. That's why it has 2 sig-figs. Let's move on to another subject. We have rounding. And what's the purpose of rounding? Why do we use rounding in our daily life, actually? All of these, let's say, in previous lectures, I told you about for example, prefixes. I told you prefixes are used for simplicity, for simplifying our speech. And rounding is used for, one of the usage of rounding is for simplicity. One of the using of, for example, rounding. Maybe think about a student. The average number of a student, average mark of a student, maybe is, let's say, 19 point, for example, 82. The average mark. Whenever the person's, let's say, ask asks him or her, how much is your mark in how much is your mark in physics, in every whatever subject, actually he or she says 19.8, for example. It doesn't say 19.82. And maybe he or she says, I got 20, right? And he or she is right because he or she used the rule of rounding, right? So rounding is used for simplicity, especially, and unconsciously we deal with rounding in our daily life. Unconsciously, if for example, if the time is, for example, 2.2, let's say 2:58. You don't say 2:58. You say the time is 3 o'clock, for example. You don't say the time exactly. This is called rounding. You round it to a nearest number. This is called rounding, right? This is, in general, an explanation of rounding. Let me read the rounding for you. It says removing some digits uh, of a measurement according to a certain rules. We have a rule here as well, like significant figures. We cannot drop the figures randomly. We have a rule, right? Rounding is a systematic method, actually, such that the measurement contains the required number of significant figures, right? So in general, simply we can say rounding is dropping some digits, skipping some digits from the, let's say, from the measurement based on the certain rule. Let's move on to the rules, actual rules for rounding. We have two rules for rounding. Either we have round down or we have round up. What do I mean by round down? What do I mean by round up? About the round down, right? When do we use round down, actually? When, in this situation, if the digit ends at 0, 1, 2, 3, or 4. You have a digit, if the digit ends at these numbers, so we use round down. So what's the meaning of round down? It says drop the last digit, only drop the last digit, that's it. So right now, let's say, focus on these examples. 21.5. We want to round it. How do we round it? Because the number ends with what? Ends with 0. That's why just drop the 0, and it will be 21. Number 2, 78.4. 78.4. It ends at 40. It's at 4. Excuse me. Just drop the 4. It will be 78. 99.92. It ends at 2. Just drop the 2. It will be 99.9. And this one, 0.11, the number ends with 1. Just drop the 1. And it will be 0.9, 0.1, right? So this is the first rule. This is the first rule about the rounding. How do we use round up? When do we use round up, actually? If the digit ends at 5, 6, 7, 8, or 9. Take a look at these, let's say, these figures. Whenever the figure ends at 5 and above 5, actually, 5, 6, 7, 8 till 9, whenever the figure ends at this one, drop the last digit, drop them, but the situation is different from the previous case. In round up, we have to obey this note. Drop the last digit, then add 1 unit to what? To the penultimate digit. What do I mean the penultimate digit? Means the digit before the last digit. Drop the last digit and add, let's say, 1 unit to the penultimate digit. Let's solve these problems. Number 1, the question, let's say, the first example, 123.9. We want to convert it. We want to round it. So we have to Shall I use round down or round up? Think about it. The number ends with what? It ends at 9. That's why drop the last digit. I dropped it, no problem. But here I, let's say I add 1 unit to the what? To the penultimate digit. It will be 124.0. Or if you are not satisfied with this one, if you don't prefer it, just write 124. That's it. 124.0 or 124. Question number 2, 3.1415. We want to, let's say we want to round it. Because the number ends at 5, the number ends at time, and that's at 5 actually. Drop the last digit, but add 1 unit to the what? To the penultimate. This is penultimate digit or the digit before the last digit. It will be 3.142, like this. 0.78, I'm sure you know it better than me in this situation. Drop the last digit. We have a round up here. Drop the last and add 1 unit to the digit before the last digit. It will be 0.8. About this one, this example is different from other examples. We have 0.96, right? This is the last digit. The number ends at 6. So we have round up. You know this information. We have round up, just drop the last digit. We eliminate it, actually. Eliminate it. We drop it, we skip it. But here, whenever you add 1 unit to the penultimate digit, to the 1, to the 9, 9 plus 1 becomes 10. In this situation, you have to write 0 here. You have to put decimal point. So in this situation, the 1 is carried over, yeah? Carry over the 1 to the 0. I want you to carry over the 1 to the 0. It will be 1.0. Or we can say 1, right? It's about the rule of rounding. So we had two rules. Either we had, let's say, round down or round up. In the case of round down, if the number ends at 0, 1, 2, 3, 4, just drop the last digit and write the rest without changing. Right? About the round up, the number ends at 5, 6, 7, 8, and 9, right? Drop these numbers, but put, let's say, add one unit to the penultimate digit. Let's move on to another subject. We have another table. The table talks about what? This table talks about calculating significant figures, right? Rules for calculating with significant figures. Maybe you have an operation. We have a mathematical operation. You have a multiplication or division or addition or subtraction, whatever operation you have. In this situation, after you calculate let's say, the operation, after you do the calculation, actually, we want to determine the significant figure, right? Here, I want you to keep in mind that math is first, actually. Do the math first. After that, let's say, goes to the counting of significant figures, right? Do the operation firstly. After that, we determine the significant figures. About for example, addition and subtraction, we have a rule here. About the addition and subtraction, the final answer should have the same number of decimal places as a measurement with the least. Look here, with the least. Excuse me, let me mention it here. With the least what? With the least number of decimal places. If you have addition or subtraction, so the answer, I told you, actually calculate the do the let's say operation, calculate the result, you get the number. Yeah, this is the result. This is the rule actually. Obey this rule for determining the, for rounding actually, for rounding the uh, result of the calculation. The final answer should have what? Should have the same number of decimal places as a measurement with the least. Which one among these figures actually? Which one has the least decimal places actually? This one, yeah? This one has only one decimal place. That's why the last number, the last answer should have only one decimal place. What does it mean? You have to round it, let's say, we have to round it to a certain figure. For example, after you calculate the, uh, uh, after you calculate the addition actually, after you do the operation, you get this number 103.15, 103.15, right? Focus on the number with the least decimal place, with the minimum decimal places. So the answer should be what? Well, the answer should be, let's say, the answer should have only one significant figure. That's why you have to round it up here, because the number ends at 5. Drop the last digit, we dropped it. After that, add 1 unit to the penultimate digit. The answer will be 103.2. Another one. So we obey this rule in the case of addition and subtraction. Focus on the focus on the figure with the least decimal place. Number 2, second example, 7.58 minus 2.16. We want to subtract 2.16 from 7.58. After you do the operation, after you find the result, right now, which, let's say, figure has a minimum decimal places, has a minimum decimal place, excuse me. Which figure? Both of figures have what? Have 2 digits after the decimals. So the answer, the final answer should have, let's say, should have 2 decimal places. But here, in order to round it actually, in order to round it off, the number ends at 2. That's why we drop 2 actually. And the answer will be 5. Maybe you say, teacher, the answer will be 5.4. But if you write 5.4, your answer is not correct because you didn't obey this rule. You have to obey this rule. The answer should contain what? The answer should involve, let's say, 2 decimal places, right? So here, instead of this, for example, situation, in the case of these cases, just write the 0, let's say, at the end, yeah? Just put the 0 at the end. So we solve the problem without changing the number, actually. Whenever you put 0 here, after the 4, the number as value, actually, the number as value remains as it is. You didn't change the number, you just, let's say, added 1 0 after the decimal point in order to actually coincide with the rule, in order to obey the rule. Let me read another one about multiplication and division. We have another rule here. For multiplication and division, focus on what? Focus on the number with the least significant figures, not least decimal place, right? Let me read the rule for you. For the case of multiplication and division, we obey this rule. The final answer should have the same number of significant figures as a measurement with the least number of sig-figs. So keep in mind that in the case of multiplication and division, focus on number of sig-figs, not number of decimals actually. Focus on the number with the least number of sig-figs, with the minimum number of sig-figs. Let me read the, let's take a look at these examples. Example number 1, 123 multiplied by 5.35. After the calculation, you get this number. This is the result. The result should have what? Excuse me. The result should have, let's say, should have the significant figures as the minimum, as the number with the minimum significant figure. Which one has a, let's say, minimum significant figure? Which one has the least significant figures? Actually, both of these numbers have the same significant figures. So both of them have 3 significant figures. The answer should have 3 significant figures, right? But here, after the calculation, after you find the result, you obtain what? You obtain 658.05. So this number contains what? Contains 5 significant figures, right? It contains 5 significant figures. That's why you have to round it off to what? You have to round it off to the 3 significant figures. How do you round it off, actually? You have to focus on these 3 figures. Just choose these 3 figures from the left side and drop the 0.5. The situation and the answer, it will be 658, right? About the division, we have the same rule actually. Multiplication and division have the same rule. 2.5 divided by 0.2, right? The result will be 12.5. Look here. 12.5 contains 1 significant figure. Contains 3 significant figures. We have 3 because they are non-zero. I told you non-zero digits are significant without thinking. So here, I told you in multiplication and division, we focus on the number with the least number of significant figures. Which one has the least sig-figs actually? This one. This one has least sig-fig. Only it has 1 sig-fig. That's why the answer should contain 1 sig-fig. So how is it possible? What happens to the result? If I, for example, drop this one and add 1 to the 2, actually, it will be 13, right? It will be 13. If you get this number, actually, if you say the number is 13, right? The answer is 13. Your answer is wrong because you didn't obey the rule. The result should contain, let's say, only 1 significant figure, right? In this situation, instead of this 3, right? Let's say I put instead of this 3, I write 0. In this situation, I can say 12.5 turns to what? Turns to 10. 20, let's say 12.5 rounds to 10. That's all for today. Thanks for watching this video. I'll see you in next video, and bye for now.